Okay, it's 11 o'clock. Let's get started. Hello, everyone. Thank you for attending today's CGD seminar. I'm Jiang Zhu. I'm filling in for Dan, who is out of town today. So before we get started, I want to remind everyone our CGD code of conduct. At this seminar, we offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. Also, I will ask everyone, please keep yourself muted during the seminar and hold your questions until the end of the talk, unless you have clarifying questions. And it's my pleasure to introduce today's speaker, Isla Simpson. Isla is a scientist too at the climate analysis section here at CGD. Isla is also a co-chair of CESM Climate Variability and Change Working Group. Isla got her PhD in atmospheric physics in Imperial College London in UK. Isla did her postdoc research at University of Toronto and later in Columbia University before joining NCAR CGD in 2015. Isla's research studies the large-scale atmospheric dynamics and its representation in global climate models. She works to understand the dynamical mechanisms involved in the variability and change of the large-scale atmospheric circulation and the impact on regional and hydroclimate using a hierarchy of modeling approaches. Title of her talk today is, What Should We Expect for the Future of North American Hydroclimate? Isla, the floor is yours.
Okay, thank you. Okay, slides look good? Okay.
Yes.
All right, thanks. So yeah, this talk is going to be about what we can expect for the future of North American hydroclimate. It's actually going to be a little more specific than that. I'm going to focus mostly on the US Southwest, which is of course where most of us live. And it's a region that is extremely vulnerable to change. And we've already seen changes and we're going to continue to do so. And we're going to see impacts on our water resources and on wildfire occurrence. And of course, we were made very aware of wildfire impacts just a few weeks ago. So this is the Marshall Fire. This is a picture that was taken by John Pizzullo from the Mesa Lab, and this affected many people here. And of course, there are a number of reasons why this fire happened and why it was so destructive, but almost certainly one of the contributing factors is that it was extremely dry for that time of year. So I want to start by talking about 2020, which was kind of extreme in a number of ways, one of which is what happened in the US Southwest hydroclimate. So I'm currently leading the NOAA Drought Task Force with Justin Mankin and Andy Hoyle and Rong Fu. We're all co-leads. And we produced this report that came out late last year, kind of characterizing the drought that happened in 2020 and is actually currently still ongoing. So I'm going to start by kind of going over my contribution to this report, which was to place what happened in 2020 within the context of what we expect based on our Earth system models. So we're going to start by looking at annual averages here over the 6 states of the US Southwest, so just January to December averages. And here I'm just showing observational records. So we've got precipitation on the left and surface air temperature on the right. And these are anomalies from the 1950 to 2000 average. And so you see that 2020 was extremely dry. It was the driest year on record going back even to the 1890s. And it was also very hot. And so let's consider then what would be our expectations of having a year like 2020 based on what our Earth system models do. And so for this, we're going to use the Couple Model Intercomparison Project Phase 6 models, so 33 different models going into this analysis. And we'll use this high emission scenario, although actually out to this kind of time horizon, it doesn't make a huge difference which scenario you use. So here I'm just plotting all of the model members, and then we can look at the ensemble mean to get an indication of what the models say the force response is. And so they say over the historical record, on average, we haven't really seen a forced change in precipitation. But that's not true for temperature, of course. We see this clear increase in temperature, which is very aligned with what we've seen in our observational record. So I want to talk about 2020 from the perspective of two quantities here, precipitation and then near surface vapor pressure deficit. So if you're not familiar with VPD, it's the difference between the saturation vapor pressure and the actual vapor pressure. So it's the difference between how much water vapor the atmosphere can hold and how much it actually has. And if you have a higher VPD, you'd expect you'd have more evaporation if you have water available. And so how much water vapor the atmosphere can hold, that depends on temperatures. You might expect an important role for forced climate change coming in, at least through this part. And there are very clear connections between VPD and wildfires. And we heard about this from Jackie last week at the CGD exchange. And this is one of the figures that she showed. So this is over the US Southwest, it's relating in each year the burned area to VPD. And so you can see, first of all, this is not a linear scale, it's actually an exponential relationship. And in years where you have higher VPD, you tend to have a higher burned area, like in 2020. And this other example is a case for Alaska looking at ignitions. And so what it's showing is the average VPD for the 5 days prior to ignitions. And what you see is no matter what size the fire is, you tend to have positive VPD anomalies before you have wildfires. So this is just illustrating the importance of this quantity for wildfires. So precipitation and VPD are not independent of one another. You'd expect them to be anti-correlated. So if you have a year with high precipitation, you're probably going to have low VPD because you'll have more water vapor in the atmosphere and you'll probably be cooler. And then both will be affected by internal variability, and both will also be affected by external forcings. So I want to walk you through this diagram here, which is going to show kind of the joint probability distribution of precipitation on the x-axis and then vapor pressure deficit on the y-axis. And all you see here right now are the observed years from 1950 to 2000. And everything I'm going to show here in this diagram is going to be anomalies from that baseline 1950 to 2000 period. So these years are color-coded according to the year. So we've got the 1950s in dark blue up to the 1990s in the light blue. And there's a negative correlation here, which is what we expect. So when you have a year with high precipitation, you've got low VPD and vice versa. Now, this is the model-based probability distribution, joint probability distribution. And what matters here is the relative probability. And this lowest contour, it's not zero, but it's very small outside of that area. So what the meaning of this is when it's dark colors, there's a high probability that a given year is going to sit at that location in precipitation and VPD space. And so this probability distribution is coming from the models from the 1950 to 2000 period. And so kind of reassuringly, the observations lie pretty nicely within that model-based distribution. Now, this is what has happened in the last 20 years, and you can see that we've clearly shifted out of that pre-2000 climate towards higher vapor pressure deficits. And then you've got 2020, it's kind of out on its own and pretty extreme in both precip and VPD. So we could use the models then to say, well, what would be the chance that we'd have a year like 2020 if we were in the climate of 1950 to 2000? And here I'm just going to look at the univariate probabilities, so not the joint probabilities. And so first of all, for precipitation, if we ask what's the chance of having a year with as low precipitation as 2020, we find it's about 2% chance, so about 1 in 50 year kind of event. But if you ask the same question for VPD, it just doesn't happen in the pre-2000 climate. So there's about 1,700 years of simulation going into this probability distribution, and not a single one of them gives VPD as high as what we saw in 2020. But of course, the climate is not stationary and we have had changes. And so if instead we look at the model-based probability distribution for 2010 to 2030, so centered on 2020, you can see that it's clearly shifted up towards higher VPDs. It's very aligned with what we've seen in observations. And so if we ask that same question now for precipitation, if we're looking at the 2010 to 2030 climate, the model suggests the probability of having as low precip as 2020 hasn't really changed. But if we now ask that question for VPD, it's now possible. Although it's, according to the models, it's still a pretty extreme event. It's still a kind of 1 in 200 year kind of event, but it's now possible, whereas it wasn't in the 1950 to 2000 climate. And then of course we can ask what's going to happen in the coming decades. And this is what it looks like for 2030 to 2050. Now, one thing you'll notice is that the distribution starts to become broader as we go into the future. And there may be some role for changing variability there, but I think a large part of this is because the models start to differ in what they're doing in their forced responses. But if you look at precip, there's a slight increase here, but there's definitely not a systematic change in the probability of having a low precip here. But if we look at VPD, a year like 2020, which currently is about a 1 in 200 year event, becomes more like a 1 in 10 year event by the time we're in the next couple of decades. So the models don't suggest that forced climate change has made a low precipitation year like 2020 more likely, but they suggest that a year with as high VPD was almost impossible without forced climate change. And we're going to see that happening more and more in the future. Now, of course, this drought hasn't finished. 2021 was dry too, just not quite as extreme. But you draw similar conclusions for a 2-year period, although it gets to more like 1 in 5 2-year periods in the future would look like the last 2 years for VPD. And the last decade has actually been really dry. And if you do the same for a 10-year average, you find that by 2030 to 2050, the last 10 years would be kind of the norm for VPD. And then that makes you wonder, well, what does an extreme decade look like then in the future? So what I just showed you, though, was glossing over a lot of complexity. For one thing, I showed annual averages averaged over the 6 states of the US Southwest, and there's a whole lot of seasonal and spatial variations in the responses. And so just to show you that here, I'm just showing the ensemble mean response of precipitation in the models. And you can see that while in the annual average, there's not a whole lot going on, that is not necessarily true locally or seasonally. Another big simplification, of course, was that I took all of the CMIP6 models as kind of our best estimate of how things are likely to change. And that's, I think, the best thing to do in the absence of better information. But the CMIP6 models do differ in their responses. And so just to illustrate that here, I'm just showing, similar to those maps of precip I just showed, this is just the agreement on the sign of the change. So it's not telling you about agreement on magnitude, but you can see even when it comes to the sign of the change, for example, in this summer here, which is what was really extreme in 2020, which was a failure of the summer monsoon, the models don't even agree on the sign of precipitation change there. So we can use our models to make projections like this, but do we trust them? And we obviously can't trust them all because they're all doing different things. So can we try to narrow down our uncertainties? And so if we think about what's it going to take to get climate and hydroclimate projections right for the US Southwest, here I'm just listing kind of factors that I see as being kind of leading order, and there's obviously more than this, but we need to get many things right to get this correct. And they're all coupled to one another. So this is really why we need Earth system models to be answering this question. And so I'm going to spend the rest of the talk here going over 2 of my contributions to this puzzle. So the first is about large-scale circulation projections and how they connect to precipitation change. And then the second is some newer work, which is pointing out, I think, a potential deficiency in our models, and it's ongoing, so we're not totally sure what is deficient, but there's a high likelihood that it's related to something in the representation of the land surface. So I'm going to start with the first of these, which is attempts to constrain precipitation projections based on large-scale circulation projections. And so this is really actually revisiting some of my older work. And the reason I wanted to do that was to kind of see, does it stand the test of time? And also I wanted to be more quantitative than we were in this original paper about how much we can actually constrain things. And so this work is presented in this paper, which came out last year, that I led together with this group of people, most of whom got together at a CMIP6 hackathon. So it's about wintertime precipitation changes by the end of the century. And so here you see the CMIP5 and CMIP6 ensemble means, and they look pretty similar. But if we dig a little deeper and we just look at averages over the West Coast and the South, you can see that even though I showed there was actually pretty good agreement on the sign of the change here, for the most part, there's a large spread in the magnitude, and that spread is larger than what you'd expect based on internal variability alone. What you'll also notice here is that in the US South, there's been a shift from CMIP5 to CMIP6. We have less ensemble spread in CMIP6, and the mean has shifted from being a slight drying to a slight wetting. And hopefully I'll convince you that we can kind of understand this change, and it's because the models have improved. So the topic here is trying to constrain this precipitation uncertainty through understanding the intermodal spread in the large scale circulation. So here we're going to be looking at stationary waves, and we'll look at this here through the upper tropospheric meridional wind. So this is the present day climate, and this is the future minus past difference in CMIP5. And so what it shows is that in the response, we end up with this kind of southerly, northerly, southerly pattern over North America. Now, if we just take as an index of the magnitude of this response, we'll just take the average of the meridional wind over this box here in the US Southwest. And you can really think of that being an indication of the magnitude of this whole wave train structure. And there's a large spread in the magnitude of this response across the CMIP5 models. And if we go and correlate that with precipitation change, this is what we get. And so this is multiplied by -1. So we're looking at it from what do you get with a larger amplitude of this whole wave train structure. And you see this pattern, and it's because these waves are barotropic, so they're associated with low level flow that's kind of bringing in moist southerlies toward the US West and then bringing in dry northerlies toward the South. So that correlation pattern makes sense. So in this first paper, we propose a mechanism for why we get this change. And I don't want to dwell on the details here, but I want to go through that to kind of set the stage. So first of all, we showed that if you filter that meridional wind field to get rid of the largest scales, you retain only the zonal wave numbers greater than 3. They're a pretty small part of the present day climate. You've got these waves, they're kind of produced around East Asia, and they're meridionally trapped and they're zonally propagating across the Pacific waveguide. And while they're a small part of the climate, they're really dominant in this response over North America. And we did some stationary wave modeling, and that revealed an important role for the change in the zonal mean zonal wind in producing this response. In particular, the strengthening of the subtropical upper tropospheric westerlies was found to be important. So if we just take an average here over this latitude band, and this is showing the same longitudes as you see in this map, so it's kind of mapping out the present day wave structure. If we use stationary wave theory, it tells us that the waveguide is only going to support stationary waves that have a total wave number that's less than this stationary wave number. And it has zonal and meridional components, and it depends on the zonal mean zonal wind and the curvature of the zonal mean zonal wind. And so what we argued is that under climate change, you get that strengthening of the subtropical westerlies, and that leads to a decline in this stationary wave number, which means that the waveguide is going to not be able to support the smallest scales as well, and it will be better at supporting the larger scales. And to just kind of see this in a qualitative way, I'm just going to show you here the future wave structure in the red, and you can see that it's kind of stretched out compared to the black, and that's because this waveguide has changed in its ability to support the different scales. And so what that means is that by the time you're downstream here over North America, you end up with this southerly, northerly, southerly pattern. So then based with that on that mechanism, we wanted to explain why do we get this spread in the response. And so we argued that we'd expect the change in the meridional wind over the US Southwest to be proportional to the amplitude of the relevant waves in a model's present day climate. So we just took as a measure of the amplitude of the waves, we just take the root mean square amplitude of the meridional wind over this box region here. And indeed in CMIP5, we found a relationship. So you got the present day stationary wave amplitude on the x-axis, and then the change in meridional wind on the y-axis. And they're related in the way you'd expect. A model that has larger amplitude stationary waves tends to show a bigger response in the meridional wind to climate change. Now here's where the observation-based estimate of the stationary wave amplitude sits, and you can see that many models are biased and have stationary waves that are too large amplitude. And so this offers the potential for an emergent constraint where you could say most likely we'd expect that maybe the real world is sit somewhere at the intersection of these two lines. So as I said, I wanted to revisit this for a couple of reasons. So one is to see, does this still hold in CMIP6? And also a large part of what we did in this paper was to propose a methodology to be more quantitative about how much we can constrain the future. And so we propose a method to account for all the different uncertainties. And I won't go into the details, I'll just kind of show you the results here. So first of all, here's our kind of raw meridional wind changes for the CMIP5 models. And this is what our constrained projection would say. It would say, most likely we'd see a smaller change in the stationary waves than what we get from the ensemble mean. There's still a pretty large uncertainty, but we can say that these models that show this really large change are pretty unlikely. So now what's happening in CMIP6? So here's where the CMIP6 models sit. And the relationship is still there. There's still a significant correlation, but you can see that many of the models have improved. We have a much smaller ensemble spread in CMIP6, and they're closer to the observed stationary wave amplitudes. And so when we go and look at our CMIP6 responses and the constraint, we see that we have a smaller intermodal spread in the change in the stationary waves. The mean has shifted to being slightly smaller than it was before, closer to what our constraint suggests. But we also see now that because we have less spread and we have pretty large uncertainties in our constraint, it's perhaps not so useful moving forward now. So for the stationary waves, I'd argue that the constraint on the amplitude of the stationary wave response has stood the test of time. And it can kind of help us to explain some of these changes we see from CMIP5 to CMIP6. But who cares about upper tropospheric meridional wind? I think the question here is really, is this going to be useful to constrain precipitation? So here's the correlation we had in CMIP5 between the present day stationary wave amplitude and precipitation change. And what it shows is that models that had a larger amplitude stationary waves, so more wetting on the US West Coast and more drying in the US South. So that's a potential constraint because we know that larger amplitude waves are more biased. But this is what we see now in CMIP6, and that correlation structure has gone away. And I think it's not because this was wrong or a statistical fluke. It's because this was being really helped out by some really biased models in CMIP5. So here's our correlations between precipitation and stationary wave amplitude for the West Coast and for the US South. And you can see how much these really biased models were really helping us out here to give us this significant correlation in CMIP5. And if we go ahead and recalculate the correlation, excluding the models that have a larger bias than the maximum in CMIP6, you can see that it's also not significant in CMIP5. So what about being quantitative on this constraint for precipitation then? So this is for the US South and the relationship we had in CMIP5. And this is what our constrained projection would say. It would say that rather than have a slight drying like the ensemble mean here, we would more likely see a slight wetting, pretty large uncertainties, but we can rule out some of those models that have a really large drying in the US South. Now here's where CMIP6 is, and it doesn't really make sense to be using the constraint anymore in CMIP6 because there's not a correlation. But this is what it looks like. And so you can see that kind of as the models have improved in their stationary waves, the response overall has shifted to be a slight wetting, and there's a much smaller ensemble spread. And we no longer have the models that produce this really large drying over the US South. Now for the US West Coast, though, this is a case where quantifying those uncertainties is really important. And it wasn't something we did in the original study. So we have this relationship, but you can see there's so much scatter around it. It's going to be uncertain. And so this is what our constraint would have said in CMIP5 if we had quantified it properly. And you can see that there's a really large uncertainty to the point that it almost encompasses all of the models. So when quantifying the uncertainties properly here, we find that even in CMIP5, where a significant correlation existed, it's not a very useful constraint quantitatively. And that's how it looks now in CMIP6. And of course, now that correlation has gone away. So the conclusions for this part are that we can understand the mechanisms behind the projected changes in the winter stationary waves over North America. And through that understanding, we can relate the intermodal differences in the amplitude of the response to their representation of present day climate to constrain future projections. And this relationship between present day stationary wave amplitude and climate change has stood the test of time. It's still there in CMIP6, and it can explain why the CMIP6 response is smaller on average with less intermodal spread. It's because our models have improved. For precipitation, over the US South, I'd argue we did have a quantitatively useful constraint in CMIP5, and it can help us to understand how the model ensemble has evolved in CMIP6. Our models have improved, and that's overall led to less drying and less ensemble spread. But over the US West Coast, when we properly quantify our uncertainties, we see that they're very large. And so even in CMIP5, this wasn't a very quantitatively useful constraint there. So we still have a long way to go to constraining our precipitation projections. We still need to understand origins of the remaining intermodal spread in the winter. And we also need to be thinking about other seasons too. So now I want to go on to the second part, which is newer work. And it's probably going to be raising more questions than providing answers. And I think it's probably related to something in the land surface, but that's kind of yet to be determined. So the topic here is about vapor pressure trends over the US Southwest, and I'm concerned that we're getting something seriously wrong. And it's actually more general than the US Southwest. It's for arid and semi-arid regions of the globe. And so I want to acknowledge collaborators here, in particular, Karen McKinnon, who's helped me to think through a lot of what I'll talk about, and Daniel Kennedy and Dave Lawrence, who I'm actively working with at the moment to try to understand potential origins of this issue from the land surface. So at the beginning, I showed this diagram of how VPD has evolved over the historical record and how it's kind of consistent with what we see in the models. But this trend toward higher VPD has two parts. It has a part that's related to the saturation vapor pressure, which depends on temperature. And it has a part that's related to the actual vapor pressure, which is dependent on how much water vapor you actually have in the atmosphere. Surface pressure comes in here too, but that's not important in the trends. So I want to decompose these US Southwest trends in VPD into those two parts. And so we'll look at annual averages here from 1980 to 2020. We're looking at the trends over that 41-year period. Again, averaged over the 6-state region of the US Southwest. So what you're going to see here on the x-axis is the actual vapor pressure trend, and on the y-axis will be the saturation vapor pressure trend. And the difference between these is the VPD, which will be given by these gray contours. So we're going towards higher VPDs toward the top left of this diagram. So here's where ERA 5 reanalysis sits. And so it suggests we've had an increase in the saturation vapor pressure and we've had a decrease in the actual vapor pressure. And this is not sensitive to including 2020. That's what you get if you go to 2019. Now here's what all of the individual models of the CMIP6 ensemble do. And each model is a different color and they all have a different number of ensemble members. And you can see that for saturation vapor pressure, ERA 5 is pretty nicely within the model distribution. But for actual vapor pressure, it's not. So the models kind of overwhelmingly suggest we should have seen a positive trend in vapor pressure, but the reanalysis has shown a decline. And so for VPD then, we do have ensemble members that have as big of a VPD trend as what we've seen in the reanalysis, but it's for pretty different reasons. So they're doing it with a big increase in the saturation vapor pressure, which is the temperature part, that's compensating for not having this decline in the actual vapor pressure. Here's what CSM2 looks like. So this is the 100 members of the large ensemble, and a pretty similar story there. And this is what you get in CSM2 if you prescribe observation-based SSTs. And so this shifts you to being more likely to have a low vapor pressure trend, but it certainly doesn't get you to what we've seen in ERA 5 here. So our models seem to come nowhere close to simulating this Era 5 negative vapor pressure trend over the US Southwest. I just want to show you the seasonality of this. So just to kind of set the scene here, this is the climatology of vapor pressure. And so you have more water vapor in the atmosphere when it's summer, when it's warmer. There is a mean bias in the model, and I'm not certain, but I suspect there's a role for surface pressure actually coming into that and not resolving the topography completely. But the point here really is this, which is the trend in vapor pressure for each month of the year. And so you see that for each month of the year, the reanalysis trend lies outside of the CSM2 distribution. It's bigger in the summer, but that's also when you have more water vapor. And so if we look at it as a percent trend of the climatology, it's pretty uniform throughout the year that you're having this decline in water vapor while the model is showing an increase. This is just the vertical structure of specific humidity trends. This is on sigma levels over the US Southwest, so kind of terrain following, just to show you that the discrepancy is largest at the surface, but it's kind of there throughout the whole of the lower troposphere. So one big question then is, do we trust Era 5 vapor pressure trends? The reasons we might not, you have issues in the underlying forecast model, you'd have inhomogeneities as you start to introduce different observations at different times. So this is a map of the Era 5 vapor pressure trend, and you can see that there's this big decline here over the US Southwest. And this is what the raw station data look like. So this is the ISD stations, they're mostly at airports. And you can see that they look very similar to Era 5. So that's reassuring. I mean, they're not independent because Era 5 is assimilating station-based measurements of humidity, but it's reassuring that we can see the same thing in the raw station data. That being said, it is not there in other reanalyses. So this is what JRA 55 looks like in MERA 2, and they don't show the same degree of decline in atmospheric vapor pressure over the US Southwest. So if we're quantitative about it here, I'm just showing that the area average trend over our 6-state region. And you can see that there's really good agreement between Era 5 and the stations, and they lie outside of the model distribution. So I'm going to trust Era 5 because it looks like the stations, and I'm trusting the stations, of course, open to any suggestions for reasons we might not trust the stations, but at this point, I don't think we have any reasons to do so. So let's think then about what would lead to trends in atmospheric water vapor over the last 4 decades. Well, we'd have the role of external forcing, and then we also have internal variability. And so I want to start by thinking about the thermodynamic impacts of rising greenhouse gases and what we would expect that to do to water vapor. So we're ignoring circulation changes for now. How would we expect water vapor to change as we warm under increasing CO2? Well, our atmospheric moisture budget, it tells us that the rate of change of vertically integrated moisture, it's a small residual between these large terms that are close to balancing. We've got evaporation, and by this I mean all water flux from the surface to the atmosphere, so including evapotranspiration and everything else. Precipitation, and then we've got the vertically integrated moisture flux convergence. So in equilibrium, we have that P minus C is equal to the vertically integrated moisture flux convergence. And then over land, if we're in equilibrium and we're in the annual and the climatological average, and we're on scales that are large enough, so kind of larger than the catchment of a river, P minus C has to be greater than 0 or greater than or equal to 0 because you don't have negative runoff. And that means that land regions are typically regions where you have a net convergence of moisture. Now, we're going to be warming, and a warmer atmosphere holds more moisture. So let's think about kind of the simplest leading order effect we might expect to see. So if everywhere were to warm at the same rate, and water vapor were to increase everywhere following fixed relative humidity assumptions, so following our Clapeyron scaling, we'd expect that atmospheric water vapor would increase at about 7% per Kelvin. And so if we reached a new warmer equilibrium where this was happening, over land, it would be a region where you'd have an increased convergence of moisture. You would have accelerated your hydrological cycle. There'd be more water vapor in the atmosphere. Regions that are climatologically regions of moisture convergence would get more water vapor. And so you'd expect to see an increase in P minus E. So a warmer atmosphere over land, you'd expect more convergence of moisture, and you'd expect that that will be kind of helping to maintain this increase in humidity of about 7% per Kelvin. But this is probably not going to happen over land, because land warms faster than other regions. And so other regions where the moisture is coming from, the water vapor might not have increased as much as what you'd need to maintain that Clausius-Clapeyron scaling over land. So our increased moisture transport into land regions might not be as big as we'd expect. So then to try and keep up with that increased demand, if you have water available at the surface, you might expect you'd see increased evaporation to try and keep up with the increased atmospheric demand. And then of course, you'd also have plant physiological effects, and that could act to reduce your evapotranspiration. So how all this is going to work out is not totally clear, and that's what our models are aiming to figure out for us. But we'd expect that overall, maybe we'd see an increase in water vapor, but not as much as 7% per Kelvin. It depends the extent to which these other sources can help to keep up with the demand. And of course, if we increase evaporation and if our P minus E actually declines, then we'd expect to see drier surface soils. So kind of our leading order expectation based on the thermodynamics then is we'd expect to see an increased atmospheric water vapor, but maybe not as much as Clausius-Clapeyron scaling. Increased evaporation, assuming you have water available and your plant physiological effects don't overrule. A smaller P minus E increase than Clausius-Clapeyron would suggest, and it may even decline because of this importance of the evaporation. And then we'd also see drier surface soils if P minus E declines. So let's look then at what the model actually does. So we'll look at the ensemble mean here of the CSM2 large ensemble to look at the force response. So here's what the model vapor pressure does. And so it's pretty clearly showing an increase that starts around 1980. This is what we'd expect based on Clausius-Clapeyron scaling. So it's not quite at Clausius-Clapeyron scaling, but it's like not too far. This is what precipitation and evaporation do. So you can see that evaporation starts to increase in the late 20th century. Precipitation, though, is kind of steady, but then it starts to increase. And so if we zoom in on the 1980 to 2020 period, you don't see too much trend in precipitation, but you see a pretty clear increase in evaporation. So in the model, P minus E is indeed declining, and runoff declines too, but it doesn't totally balance this. And we do see a net decline in our surface soil moistures in the model. So thinking about kind of our expectations for what we think would happen, we see exactly this happening in the model, which is maybe not surprising because the papers that have discussed this have to a large extent been using models to come up with these arguments. Now, on top of that, we can have circulation changes, and they could be through either the dynamic response to forcing or internal variability. And so if now we don't ignore circulation changes and we think about what can happen there, if we had an increase in convergence of moisture through circulation changes, you'd expect that would be associated with an increased precipitation, wetter soils, more evaporation if we're in a moisture limited region, and more water vapor in the atmosphere, right? Typically, you'd think if you have a time where you have more precipitation, there's going to be more moisture in the atmosphere. So I'm kind of making the artificial distinction between these things, but they're obviously connected to one another. And so now I want to separate out the vapor pressure trends that are associated with precipitation trends from those that are not. And I'm kind of thinking of this as a crude way to isolate the kind of thermodynamic effects of the increased atmospheric demand and moisture holding capacity of the atmosphere. So let's first think about what we'd expect. So suppose we're looking at the large ensemble here, what would we expect the distribution of ensemble members to look like? And we look at vapor pressure trends against precipitation trends. Well, if we had no global warming, we'd maybe expect it to look like this. So a model member that shows an increase in precipitation would show an increase in vapor pressure and vice versa. But if we add the force signal on top of that, maybe we'd expect this whole thing to shift up to higher vapor pressure trends because of that increased ability of the atmosphere to be holding moisture. This is assuming no forced precipitation change, but of course, if you had an increase, maybe it would look like this, or if you had a decrease, maybe it would look like this. So this is kind of what we expect. And now if we go and look at what the large ensemble is actually doing, so this is after removing the ensemble mean, so we're just looking at the internal variability here. For the trends over the last 4 decades, we see by construction, it's centered on 0, but we see that members that show positive precipitation trends show positive vapor pressure trends and vice versa. But if we add in that external forcing, so we add in the ensemble mean, we shift this whole distribution up toward positive vapor pressure trends in the model. This is what we get with prescribed SSTs. It makes you more likely to have negative precipitation trends and lower vapor pressure trends, but still kind of within the coupled distribution. And here's what the CMIP6 models do. So we see this correlation between vapor pressure trend and precipitation. And in addition, there's this whole shift up to having positive vapor pressure trends in the models. Now here's where the observations sit, and I'm using a variety of data sets here over the US Southwest. And you see that over the US Southwest, we actually have had a pretty extreme precipitation decline over the last 4 decades. And Flavio has a nice paper that discusses the role of sea surface temperature trends in the tropical Pacific and contributing to this. And indeed, you can see that we're kind of shifting the probabilities toward having lower precipitation trends when we prescribe observation-based SSTs. But it still lies within the model distribution for precipitation, but when you look at the vapor pressure, it does not align with what we'd expect based on the model distribution. The vapor pressure trend is more negative. So we have kind of 2 possibilities here. One is that maybe this relationship between whatever causes precipitation trends and vapor pressure trends is misrepresented in the models. Maybe it should be steeper, and this negative precipitation trend that we've seen should be more accompanied by a negative vapor pressure trend. The other possibility is maybe that this forced kind of thermodynamic increase in water vapor in the models is incorrect, or it could be some combination of the 2. So to try to distinguish between these possibilities, I want to take a step back now and look at things globally. So far here, I've just been showing you the Southwest. So here are the vapor pressure trends in era 5. And here in gray, I'm just shading out regions where the reanalysis trend lies within the model distribution. So you have a number of regions where the trend pops out as being more negative than what you get in any of the model members. And there's not really any regions that are positive here. But we can also account for what's happening with precipitation. Precipitation trends will be doing all sorts of things all over the place, probably largely because of internal variability. So I'll show you how we're going to take that into account. And so if we just take a grid point over South Africa here, this is the relationship between vapor pressure trend and precipitation trend. And whatever way you look at it here, the observations lie outside of the model distribution. But suppose the observations were here. If you were to just ask simply, does this have a more negative trend than any of the members of the models, you'd say no. But if you account for the fact that it is doing this with a positive precipitation trend, you'd say yes. So to kind of take into account what precipitation is doing, what we're going to do here is take this relationship. We'll calculate the residuals from that regression line and calculate their standard deviation. And then we'll add on plus or minus 2 standard deviations about this regression line as kind of our uncertainty range, where we expect kind of 95% chance to sit within this gray shaded range. So instead of looking at the actual vapor pressure trend now, we're going to look at the difference from what we predict using the models based on precipitation. And so if our observations were here, you can see that now if we account for the precipitation trend and ask, are we outside of this gray range that we'd expect? Now we'd say yes for this particular point. So here on the right now, I'm showing that difference from what we predict based on precipitation. And so now there's a couple of regions that are actually positive. but overwhelmingly they're negative, and there's a much larger range of the globe that is lying outside of our expectations in the sense of having relatively negative vapor pressure trends compared to what the models suggest. So now I want to divide up the planet into different levels of aridity using this aridity index. And so we can divide it up into humid regions, arid and semi-arid regions, and hyper-arid regions. And if we look at where we see this difference in vapor pressure trends from what we predict, there's a few exceptions, but for the most part, what we see here is that it's happening in these arid and semi-arid regions of the world. And so if we look at our probability distribution for vapor pressure trends across all of the arid and semi-arid regions, this is after interpolating the models to a common 1 degree grid here. This is the distribution from the CMIP6 models. And so they suggest that it's really unlikely that you'd see a negative vapor pressure trends kind of across space in these regions. And this is what the reanalysis is doing when it's pretty much 50-50. And so if we count the number of grid points that have negative vapor pressure trends, in the models, it's about 5% chance. And in the reanalysis, it's almost a 50% chance. And even if we take the most extreme model member in terms of having negative trends across spatial grid points, it looks like this, and it still doesn't come close to the degree of negative trends we've seen in the reanalysis. This is an area-weighted spatial average of vapor pressure over these arid and semi-arid regions. And so the models, CMIP6 or the CSM2 large ensemble, are showing this clear increase in vapor pressure over the last 4 decades. And this is what the reanalysis has done. And it's really not showing this increasing trend in the way that we expect. So of course, the question again is, do we trust ER5 elsewhere? I showed you what it looks like in the Southwest compared to the stations. It's a little harder other places because there's not quite so many stations, but I'll just kind of run you through the regions to convince you that I think it's looking good compared to the stations. So here over Africa, you see the stations give you negative trends over South Africa and Morocco. Over Asia, you can see kind of in Kazakhstan and Uzbekistan area and Mongolia, the stations are giving you negative trends, maybe even more so than you see in the reanalysis. Over the northern part of Argentina here, you see negative trends in the stations. And then over Europe, Spain is kind of the one arid or semi-arid region, and you see negative trends there. Australia, it's kind of difficult. There's not very many stations to convince ourselves one way or the other. So going back to this question then, now in the real world, obviously we can't look across ensemble members at one location like the Southwest. And so that makes it difficult to explore this relationship between vapor pressure trend and precipitation kind of at a particular location. But we have many spatial locations. So instead, could we use that as our degrees of freedom and look at the relationship between vapor pressure and precipitation across space instead? So one thing we can test first is we could just say, well, if we do that in the models and we look across space at the relationship between vapor pressure and precipitation, do we come up with a similar relationship to what we just see at this one location, the US Southwest? And we may not expect to, because different regions may have different relationships. But this is the model-based joint probability distribution for vapor pressure against precipitation, but instead looking across grid points. And you can see that you come up with a pretty similar relationship to what you get across members just looking at the US Southwest. So then we can go and compare this with what we see in the reanalysis, because we can actually look at this in the reanalysis. And this is what the reanalysis looks like. So, well, it's the reanalysis and it's GPCP for precipitation. So it kind of shows that no matter what your precipitation trend is, the reanalysis trend in vapor pressure tends to be lower than what we've seen in the models. So we don't have indications that that kind of relationship between precipitation and vapor pressure is steeper in the real world. Rather, we have this indication that this force trend in vapor pressure that is giving us an increase in the models through that kind of thermodynamic expectation of rising greenhouse gases, it's not happening in the same way over these arid and semi-arid regions of the world. So the arid and semi-arid regions of the world don't seem like they're seeing an increase in atmospheric water vapor that is predicted by the models or by the basic thermodynamic expectations of a rising CO2 and a warming atmosphere. So I think we need to kind of figure out what's going on here, because it could have implications for these projections, and it's not clear to me at this point really what the implications are. But it seems like historically in model world, an increase in atmospheric moisture is offsetting to some degree that temperature impact on saturation vapor pressure, which is making the overall VPD less severe. And this doesn't appear to be happening in the real world in the same way. So this is where we have a lot of open questions and what could be going on. At this point, we don't know, but one possibility is maybe the land surface has already dried out so much that we're losing that evaporative source of moisture in these arid and semi-arid regions. So it's not keeping up with the increased atmospheric demand. So what the models do is it warms, you see increased evaporation, and that's helping to maintain that increased water vapor content in the atmosphere. But presumably this can't go on forever if we start to deplete the moisture in the land surface. And so thankfully, Dave and Daniel and Sean and land surface people have a variety of ideas for potential reasons that the land might not be doing things quite as the real world. Maybe the near surface soil moistures have too much access to water from below. The land model could be too diffusive. Maybe the soil has too high a water vapor water holding capacity. And then there's these macropores, which are apparently currently not represented in the model, but if they were, maybe that would allow infiltration of the water to deeper depths. So the atmosphere wouldn't have the same access to it. It's possible that we're getting something wrong about the representation of plant water use under increasing CO2. It's not clear what that would be, and it would have to be common to all models. It's possible it's something about land cover changes, whether they're natural or anthropogenic. One example is I saw a talk by Park Williams last week. He has a forthcoming study which shows pretty clear impacts of wildfires on runoff. Whether that would be a big enough effect, I'm not sure. It seemed unlikely, but it's a possibility. Our models don't represent the intermittency of precipitation correctly. That potentially could be playing a role, but I will add that offline CLM simulations forced by observed meteorological fields look pretty similar in terms of soil moisture and evaporation trends. We could have an incorrect representation of runoff efficiency or its response to warming. Flavio again has a paper on this, and he examines biases in models, and models are biased, but it's not like they're consistently biased in one sign, and that's really what we need here, but it's a possibility. Maybe something's going wrong more on the atmospheric side, right down near the surface. Of course, we're not resolving everything perfectly, and our observations are really at 2 meters here. But I will add that if we trust our ERA 5 vertical profiles, this discrepancy is there kind of throughout the troposphere, or at least the lower troposphere. Maybe there's some kind of global misrepresentation of how atmospheric moisture transports are changing with warming, and it's a possibility alongside all of these others. So it's going to be a difficult problem to figure out, as our observations are pretty limited of the relevant quantities, but I'll just describe what we're doing right now to try to address this issue. With Daniel and Dave, we're running these perturbed physics ensemble experiments to explore sensitivities to different parameters in the land, just to get an idea of the extent to which that can perturb our vapor pressure trends. We could do a more detailed analysis of shorter timescale variability to see if we see any issues there. And there we might have some other observation-based products we can look at in more detail that are not present for the full record. I think land data assimilation could be very helpful here if we could explore how the land model behaves when it's constrained by observation-based estimates of soil moisture. Maybe we learn something. And we can just do more analysis into all of these different possibilities. So more generally, I think we need to continue doing this kind of assessment to place observed events within the context of what we expect and what we think will happen going forward. But of course, we need to be doing this with the best models that we can develop. And so we need to continue to confront our models with observations. And I think I've shown an example where there's a concern that there's something not quite right here. and we need to figure it out to know what's really going to happen. So we need to do this, especially because now we can actually start seeing the response, or lack of response in this case, to global warming. And of course, we need to continue to scrutinize our observations and know what we trust. And I've done a whole load of analysis that I haven't shared on soil moisture and evaporation products, and it's really difficult to know what is real and what is not. So that's all I have. Thank you for your time, and I'll be happy to take any questions.
Thank you, Isla, for the excellent talk. And then we have time for questions. So I will read one question from Alice. Is there any possible contribution of atmospheric PVL schemes and the resolution in that layer when the evaporation takes place?
Yeah, I think that's definitely a possibility. I guess at this point, I kind of favor the land side aspects. It seems there's more possibilities where we know that there might be things not going quite right, but I think, yeah, all possibilities are open at this point. And really the observations from the stations that are constraining things really are at 2 meters. And so, you know, is it possible that right down at the surface, the real world is really much more heavily controlled by the land than the transports, and we're not resolving that properly? Yeah, I think there's many possibilities, and that's one of them.
Okay, next. We have a raised hand from Simon.
Yeah, hi, Isla. Very, very nice and interesting talk. One question I have, we're always showing precipitation as a mean diagnostic, if I see that correctly. But really precipitation is, especially with climate change, disproportionately changing in the extreme precipitation. And we know that aridity is also not dependent on necessarily the extreme precipitation, but also on the medium precipitation that is actually seem to get actually a little weaker. We get more, you know, reduced moderate precipitation, more extreme precipitation. So, I mean, that balance between that, this could be one shortcoming in the model, that we simply don't get that right, because you could imagine the more extreme the precipitation, the harder for the land to actually absorb the precipitation. It just gets flushed away. And then again, the connection to the surface and whatever burned areas and other things. So I think that I didn't see any discussion on that. So I wonder what you think about that.
Yeah, well, I did mention the intermittency of precipitation issue at the very end there as a possibility. And I think it is a possibility, but I did add that in offline land models forced with observation-based meteorological fields, if you look at things like soil moisture and evaporation, they look the same as in the coupled model. But it's possible, and I don't know what kind of timescales the offline simulations are being forced with. So it's possible that there's still a discrepancy there in that the forcing is not high enough frequency. So I think it's a possibility, but I feel like it's more likely that if it is, there is something else going on as well. Otherwise, we would see the offline land models that are being forced with more observation-based precipitation would look different in terms of their near surface soil moisture and things. But yeah, it's definitely a possibility to investigate. Thanks.
Yeah, I agree. I mean, yeah, that was just a thought I had. Thank you.
Yeah, thank you.
Julio, you're next.
Hi, Isla. Thanks. That was very interesting. I hope this is not obvious, but what is happening with relative humidity near the surface in models and ERA? I'm wondering, diurnal cycle of relative humidity, things like that.
So diurnal cycle, I think I did look at some point into whether this was happening at a certain time of day, and I don't think it was. There is a study that has talked about relative humidity going down in particular regions of California, and that being really a nighttime thing. I think here, like, relative humidity is not going up, and it's going down over these arid and semi-arid regions. So it's not following this fixed relative humidity in terms of the trends, because the actual humidity is staying the same, but the saturation specific humidity is going up.
Thanks.
Yeah, but it's a good point. I should look more into diurnal cycles. Yeah, that's a good idea.
So we have a few more questions in the chat box. The first one, what are the model improvements from CMIP 5 to CMIP 6?
So I guess in terms of what I talked about at the very beginning, there's an improvement in the representation of stationary waves, which is leading to some small differences in the overall precipitation response, but mostly it's leading to reduced intermodal spread. More generally, I mean, there are many things that have changed. I guess within CSM, there's been big changes in the representation of the land surface. So that's one of the things that has improved a lot. And also in the atmosphere side, we've got big improvements in circulation variability over North America. Yeah, I think there are quite a lot of things, but that's a few of them that are maybe relevant for the hydroclimate.
We have two more questions in the chat box. First one, very well done talk. Does it help to think about arid, semi-arid regions as the extension of oceanic divergence zones? Do you see similar decreasing trend in the ocean divergence region?
Right. So that would be getting to the question of whether the kind of transport from the ocean regions that we kind of expect would be increasing our moisture is misrepresented. I haven't looked certainly at its salinity, but it's a good idea to do so. And I do want to look more at just kind of moisture flux convergences and divergences. I mean, there are some regions here that are pretty far from the ocean, like Mongolia. So it's certainly not just happening in regions that are close to the ocean. But yeah, it's a good idea to look at, that would be getting at this question of whether we have some kind of global misrepresentation of our moisture fluxes and transports.
Okay, one final question. Excellent presentation, very nice. Is it possible that seasonality biases play a role? Insufficient seasonal cycle leading to lesser drying in summer and fall? Or can this be ruled out because not all CMIP models have the same seasonality biases?
I don't know about the seasonality biases, so I can't say for sure. But I do feel like seasonality has to play a role in some way, because it's not obvious to me how a region that is a net convergence of moisture cannot show an increase. But it could make sense if you think seasonally that like if the evaporation is happening in the summertime, that's a time when regions like the Southwest are actually regions of moisture divergence. P-C is negative. So if you're evaporating the moisture and then you're exporting it out, then it could make sense that you've just kind of dried things out enough. And then in the wintertime, you've lost that source of evaporation. So I guess I don't know the answer to your question, but I feel like looking at the seasonality is going to be an important part of the story. And it would be easier to do if we could reproduce it in the model and then explore it that way at what the processes are actually doing. But thanks for the suggestion. I'll look at the seasonality.
Okay, there's another follow-up question. So for a single grid cell, can the land model be calibrated to reproduce the VPD trend from nearby observations? If so, the parameter change required could be instructive.
Yeah, so that's exactly what we're trying to do with the perturbed physics ensemble with SCAM. And it may not be the perfect setup because in SCAM, your large scale dynamics are prescribed in terms of what they're doing to the moisture. But we have been varying, and Daniel has suggested all sorts of parameters that we can change, and Dave as well. And so that's what we're trying to do. So far, nothing has got us to be, you can change the vapor pressure trends, but it's not bringing us down to what we've seen in observations yet. But I think there are things we can tweak about the method. That's why I didn't talk about that yet, because it's kind of still underway.
Okay, it's already 5 minutes past 12 p.m. So it's time to wrap up. Although we still have a raised hand, I'm sure Isla will be happy to respond you via email. So let's thank Isla again for the very nice talk. And thank you everyone for joining. And then we'll be back, I guess, next week. Bye, everyone.
Bye.